Hello, good morning. Hope you are all safe at home, and this is a second class. In the previous class, just introduction about solid state physics I have mentioned, and we stopped in the last class. I think 7 crystal systems and Bravais lattices. As I mentioned in 1814, for 1848, Bravais has showed that there are only 14 ways of arranging points in space to that environment look the same in space from each point in all 7 types of crystals, and they are known as Bravais lattice. In fact, the Bravais lattice is a basic building block from which all the crystals can be constructed. So he introduced the concept of a space lattice in the study of crystal structures. Usually one would expect that many lattices can be generated in 3 dimensions with different primitive and non-primitive cells. However, in 1848, Bravais has showed there are only 14 ways. Okay, he showed that there are 14 different ways of arranging identical points in 3-dimensional space, satisfying the condition of periodicity, and wherever you look, the identical surroundings should be there. Okay, so they are known as Bravais lattices, and these 14 types of arrangements, as I mentioned, they are known as either space lattices you can call or Bravais lattices. Let's take in detail about Bravais lattices. In fact, out of 14 Bravais lattices, 7 are primitive cells. Just recall, we discussed in the previous class, primitive cell is a unit cell having lattice points, that is arrangement of atoms only at corners of the cube, that is unit cells. No other points will be there either interior or at any other places. Okay, so a primitive cell is a unit cell which has number of lattice points per unit cell. So lattice points per unit cell is nothing but number of atoms or number of molecules or number of ions. So in one unit cell, only either one atom, one molecule or one ion should be present. It is possible because unit cell is represented by a cube. You have 8 corners. At each corner you have atom, but this atom is surrounded by 8 such unit cells. That means each atom is shared among 8 surrounding adjacent unit cells. So for a particular unit cell, contribution of a corner atom is only 1/8 portion. So 8 corners, 1/8 portion of 8 atoms. So 1/8 at each corner, contribution of a atom, and such type of 8 corners are there. So 1/8 into 8 corners, 8 cancels, you left with what? Number of atoms per one unit cell per cube is only 1 atom. So such a cell is called primitive cell. Okay, in another type of definition I have mentioned, primitive cell is one in which only at the corner presence of atoms will be there, no other atoms in the interior or at faces of the cube. Okay, so out of 14, 7 primitive cells are there, and the remaining 7 they are non-primitive cells. With the 14 types of lattice and the basis of primitive cell, we have totally 7 crystal systems, and those 7 crystal systems I have mentioned in the previous class with that table. Still I have retained that link. You can still refer the previous discussion, and I will remove this PPT as well as previous PPT after 2 days, that is on Wednesday. So the 7 crystal systems, if you recall: cubic, tetragonal, orthorhombic, monoclinic, triclinic, hexagonal, and rhombohedral, which is also called trigonal. So 7 crystal systems are there, and 14 Bravais lattices are there. So 7 types of crystals and the corresponding Bravais lattices with their important features or properties, they are described here. So first one, you just look at the 14 Bravais lattices. You can find the first one, cubic system. In the cubic system you have 3 Bravais lattices I mentioned. You see the first one is primitive cell. You can observe only at the corners, the presence of atoms are there, no other atom in the interior or anywhere. Whereas BCC I have written, it is body centered cubic. Apart from corner atoms, you have presence of one atom exactly at the center of the unit cell. Here FCC face centered cubic, you have 6 faces for unit cell, that is cube. At the center of each face you have presence of an atom. Okay, so non-primitive. So out of 14, 7 primitive cells are there, and remaining 7, they are non-primitive. So cubic, tetragonal, and orthorhombic, you have 4 Bravais lattices, rhombohedral, monoclinic, and triclinic, and hexagonal. Okay, there are totally 14 Bravais lattices and 7 crystal systems are there. So let's take one by one. So usually for 5 mark, if Bravais lattices along with crystal systems, if they ask, that the table is enough for a 5 mark. But for a 10 mark, you have to explain each system along with the description of Bravais lattices, because it is a essay writing. The first one, the cubic system. In cubic crystals, the important property as far as lattice parameters, that is the sides of the cube, sides of a unit cell, how they are related. We call them as primitive vectors, represented as A, B, C. So length along x-axis is A, length along y-axis is B, length along z-axis is C. So how they are related, and interfacial angles, I have given the description: alpha, beta, gamma. Okay, so in this cubic system, all the 3 interfacial angles are equal to one another, and each is equal to 90 degree, and length of primitives, that is edges of unit cell, is the same along the 3 axes, that is A is equal to B, that's equal to C, and a cubic lattice has 3 possible arrangements. So I have represented in diagrams A, B, C. So A is simple cubic. You have only at corners the presence of atoms, molecules, or ions. So it is a primitive cells. And this is BCC, that is body centered cubic. Apart from 8 corner atoms, centrally located one more lattice point is there, where you can have presence of either atom, molecule, or ion. Okay, whereas in the third diagram, that is C, you have FCC, that is face centered cubic. Apart from 8 corner atoms, at the center of each faces you have presence of a lattice point. Okay, so this is cubic system. So in cubic system, in detail I have given description here. So simple cubic is from here afterwards, in short we call it as a SC. So in the solid state physics, SC means it is simple cubic, and it is represented by P lattice. So P lattice is nothing but primitive lattice. Okay, and it has lattice points at all 8 corners of a unit cell. That's shown in the diagram. And the second Bravais lattice of cubic system is body centered cubic. In short, we call it as a BCC, and it is represented as I lattice. So notation is different, and it is a non-primitive because more than one atom per unit cell. I will show the calculation at the end. Then it is called non-primitive. So in BCC, in diagram I have shown, along with the 8 corners of the unit cell, there is one lattice point where you can hang molecule, ion or atom at the center of the body. And the third Bravais lattice of cubic system is FCC, that is face centered cubic. In short, we call it as FCC, and it is represented as F lattice. It has lattice points at all 8 corners of unit cell, and as I mentioned in the diagram, one lattice point at each of the center of the 6 faces of the cube, that is unit cell. And the important property is all the sides of the unit cell equal to one another, and all the 3 interfacial angles are also equal to one another, and each is equal to 90 degree. And a few examples I have mentioned in the previous class. The same examples I am taking here: NaCl, sodium chloride; CaF2, calcium fluoride; NaClO3, that is sodium chlorate we call. Okay, so this is first system. And second crystal system is tetragonal system. In tetragonal crystals, the crystal axes are perpendicular to one another, that is interfacial angles, each is equal to 90 degree, and the length of edges of unit cell along 2 axes are the same, and the third one along the third axis, it is other than, that is different, that is A is equal to B, that is along X and Y axis, and C, which is along Z axis, is of a different length. And tetragonal lattice has 2 possible types of arrangements. First one is the simple tetragonal lattice, which is primitive. Number of atoms per unit cell is only 1. It has only at corners of unit cell the lattice points where you can hang molecule or ion or atom. And the second type is body centered tetragonal lattice, represented as I lattice. It has lattice points at all 8 corners and one lattice point at the center of the body, BCC, that is body centered cubic. That is in cubic system we call it as a BCC, but here we call it as a body centered tetragonal lattice. It is also non-primitive. Okay, the important properties: interfacial angle equal to 90, and 2 sides are equal, the third one is not equal. And some examples of this system tetragonal I mentioned: nickel sulfide, NiSO4, and SnO2, that is tin oxide. That is the second type. And the structures are like this: simple tetragonal lattice and body centered tetragonal lattice. So it is just like a simple cubic only, but one side is different, 2 sides are equal. And here the same simple tetragonal, but at the center you have presence of one more lattice point. And coming to third system, orthorhombic system. In orthorhombic crystals, the crystal axis, that is edges of cube unit cell. They are perpendicular to one another. Again, all the three interfacial angles are equal to one another and each is equal to 90 degree, but lengths of the edges of unit cell along the three axes are different. That is, A is not equal to B and that is not equal to C. And you can expect the orthorhombic Bravais lattice has 4 possible types of arrangements, and they are simple orthorhombic lattice, which is primitive. It has only one lattice point per unit cell, in the sense it has lattice points at all 8 corners of a unit cell. And base centered, along with body centered, you have a base centered orthorhombic lattice, which is represented as a C lattice. It has at 8 corners the lattice points, as well as 2 more lattice points, one each at the base of the cube, that is unit cell, as well as at the top face of the body. That's why we call this as a base centered orthorhombic lattice. And the fourth, that is the third Bravais lattice of orthorhombic body centered orthorhombic lattice, which is I lattice. It has 8 corners, 8 lattice points and 1 lattice point at the center of the body. And a face centered, that is the fourth Bravais lattice of orthorhombic crystal system. It is a face centered orthorhombic lattice represented as F lattice. It has lattice points at all 8 corners of unit cell, and at each face you have 6 faces. At the center of each face you have one more lattice points. So 6 lattice points, one each at the center of 6 faces of the unit cell. So important property, interfacial angles equal to one another and each is equal to 90 degree, and all the 3 sides of unit cell, the cube, they are unequal. A not equal to B and not equal to C. And some of the examples which I mentioned in the previous class, the same examples I am taking. KNO3, that is potassium nitrate, and BaSO4, that is barium sulfate, and MgSO4, that is magnesium sulfate. And the structures are like this: F, G, H and I. So the first diagram you can observe no lattice points anywhere interior or at any faces, right? Whereas here it is base centered. At the bottom, that is base, you have presence of a lattice point, and at the top face you have a presence of a lattice point. That's what it is called, base centered. And here it is body centered. Along with corner 8 lattice points, you have presence of one lattice point at the center of the body. And it is face centered, 6 faces. At the center of each 6 faces you have presence of lattice point along with 8 corner lattice points. This is orthorhombic, which has 4 Bravais lattices. So coming to the fourth crystal system, monoclinic system. In monoclinic crystals, out of 3 crystal axes, 2 are not perpendicular to each other, but third is perpendicular to both of them. So the relation among interfacial angles is alpha is equal to beta, each is equal to 90 degree, and third one, which is not equal to 90 degree, that is gamma. It's not perpendicular to each other. The lengths of edges of unit cell along with the 3 axes are different, so all are unequal. A not equal to B, that's not equal to C. And monoclinic lattice. So I just make a correction. There is one mistake while typing. So two interfacial angles are equal because they are at right angles, and the third one is obliquely inclined, that is alpha is equal to beta, each is equal to 90 degree, and the third is other than 90 degree. So in this crystal, two axes are at right angles and the third is obliquely inclined, and all the three lengths of primitive vectors, that is edges of unit cell, they are unequal. It has two possible types of arrangements: simple monoclinic lattice. It has lattice points at all 8 corners, so it is primitive, and it is having the second type of Bravais lattice, that is base centered monoclinic lattice, which is C type. It has lattice points at all 8 corners of the unit cell, and two lattice points, one each at the base as well as at the top face of the unit cell. So okay, again there is a correction here. Alpha is equal to beta, each is equal to 90 degree, but gamma is different, that is two axes perpendicular, but third one is obliquely inclined. So this correction, of course in my notes I will give you the corrected one, and the examples of monoclinic Na2SO4, which is sodium sulfate, or it is also called as disodium sulfate decahydrate, and this is of course very popular iron sulfate or ferrous sulfate, FeSO4. So the monoclinic Bravais lattices are like this. The first one is P type, that is primitive, only at corners you have presence of lattice points, and here it is base centered along with the 8 corner lattice points. At the base, at the top face, you have presence of lattice points. Okay, that is the fourth system, and fifth crystal system is triclinic systems. So in triclinic crystals, none of the three crystal axes is perpendicular to one another. All are oblique to each other, that is interfacial angles are all the three, they are different and other than 90 degree. So alpha not equal to beta, not equal to gamma, and not equal to 90 degree. All the three interfacial angles are different, and lengths of edges of the unit cell along the three axes are also different, they are also unequal. So triclinic lattice has only one possible type of arrangement, and it is primitive cell simple triclinic lattice, represented as P lattice. It has lattice points only at 8 corners of the unit cell. So the examples of this type of lattice, of course the copper sulfate CuSO4 and potassium dichromate K2Cr2O7. So all the three sides of cube unequal, and all the three interfacial angles, they are not equal to 90 degree, obliquely inclined. The sixth crystal system, which is known as trigonal or rhombohedral, even sometimes it is simply called rhombic. So in this crystal, all the three lengths of unit cell, they are equal and equally inclined to each other at an angle but other than 90 degree. Okay, the angle between each pair of crystal axes is the same but is not equal to 90 degree, but the interfacial angles are equal to one another but other than 90 degree. So three lengths of unit cell equal, A is equal to B, that's equal to C, but the angles are equal to one another but not equal to 90 degree. So it has only one possible type of arrangement, which is simple trigonal lattice. So it is primitive. It has lattice points only at all 8 corners of a unit cell. And example CaSO4, that is calcium sulfate. And the last crystal system, it is a hexagonal system. So in hexagonal crystals, two of the crystal axes, they are 120-degree apart, while the third axis is perpendicular to both of them. So the two interfacial angles alpha and beta, they are perpendicular to one another, so each is equal to 90-degree, and a third interfacial angle, that is gamma, which is equal to 120-degree. So this 120-degree appear between the two crystal axes. So the length of the edges of unit cell is the same along all the axes that are 120-degree apart, but the edge along the third axis is different. So A is equal to B, the two lengths are equal, but the third one is different. So hexagonal lattice has only one possible type of arrangement, which is it has lattice points at all 12 corners of a hexagonal unit cell, and two lattice points, one each at the base and at the top face of a hexagonal prism. We call this as a hexagonal prism also. And the examples are SiO2, silicon dioxide, and AZI, that is silver iodide, that is hexagonal crystal system. And the Bravais lattice, it looks like this, hexa 6, you can observe 6 faces, that is 6 edges you can observe at the top as well as at the bottom. The angle between two axes is 120-degree, but two interfacial angles at right angles. So the shape is like this, but this is a basic unit cell. Again, it is in the form of cubic, but it looks like a rectangular because the third edge is having different length. And this type of unit cells, combination of 3 will make this hexagonal system. Okay. So two edges are equal, A is equal to B, that's what I have taken, A and A. The third is having a different length. Okay. Let's calculate number of lattice points per unit cell. I repeatedly mentioned, so lattice point is a point in the space where the basis is to be attached. So basis is a group of atoms or molecules or ions which are to be hanged to these locations. So in the examination, sometimes just to confuse the student, calculate number of ions per unit cell or number of atoms per unit cell, number of molecules per unit cell, number of lattice points per unit cell. All the 4 are the same. Okay. So the effective number of atoms per unit cell is defined as the product of number of atoms per lattice point and the number of lattice points per unit cell. It should be remembered that a unit cell is not an isolated entity, and further the lattice points do not exclusively belong to one particular unit cell, but each one is shared by several adjacent cells. I will show the diagram. The number of lattice points per unit cell in 3D lattices can be given by one simple equation. To calculate, you can use this equation. So number of atoms per unit cell in 3D lattices is equal to number of atoms present in the interior, inside the cube, inside the unit cell, plus number of atoms present at each faces of the unit cell divided by 2. Usually what happens if an atom is present at the center of each phase, it is shared because that phase is shared between two adjacent cells. So one atom is present means half the atom belong to left side unit cell, half the atom belongs to right side unit cell. So the presence of atom at each phase is shared between two adjacent unit cells. If 6 faces are there for a cube, okay, at each face you have presence of a lattice point, that is presence of an atom that is shared between two adjacent cells. So number of atoms present in each phase. So 6 phases are there, 6 atoms divided by 2, because at each phase only half of the atom belonging to the unit cell under consideration, plus for calculation of corner atoms, as I mentioned, atom or a lattice point at each corner is shared among adjacent unit cells, right? It is shared along with 8 adjacents. That's what we have to divide it by 8. For a unit cell under consideration, only 1/8 of atom or a lattice point is contributed to the unit cell under consideration. So the simple equation is a very useful relation. Number of atoms or number of lattice points present interior inside plus number of lattice points present at each face divided by 2. Now, total number of faces, how many are there at each face? If you have presence, that you have to take, plus number of atoms at a corner divided by 8. So you have 8 corners, 8 by 8. That's what 1 lattice point per unit cell. It will become a primitive. But for any Bravais lattice, you can calculate using this simple equation. That's what I have mentioned here. So number of atoms present interior at a face, at a corner. Okay. So this equation is useful. Let's calculate one by one. Unit cell with adjacent unit cells. That's what this diagram is very important. It is just a crystal structure of sodium chloride. You can observe. So you have 8 unit cells. That is 8 cubes are together. And you can observe this is the lattice point where one atom is there, but it is shared with how many unit cells? You see, this is, if I take this as 1, this as 2, this as 3, this as 4. So this is shared among the 4 unit cells at the bottom, and at the top again 4 unit cells are there. This is number 5, number 6, number 7, and this is number 8. So each atom, each lattice point of a unit cell is shared among adjacent unit cells. Okay. So you cannot have a isolated unit cell because it is a closed packing. Okay. And in each unit cell at every corner, this lattice point is shared like this. So 8 unit cells are together. I have shown here just for your understanding sake. So let's take one by one calculation. How many number of lattice points are there per unit cell in case of simple cubic? It is same as asking how many atoms are there in unit cell, or how many molecules are there, or how many ions are there in one unit cell. So the unit cell is a cube having one atom or molecule at each corner. So there are 8 atoms or molecules at 8 corners of the cube. Since each corner atom is shared by 8 surrounding cubes, that's what the previous diagram I have shown. So share of each cube comes to 1/8 of an atom contributed to the unit cell under consideration. So total number of atoms is now equal to 8 corners are there at each corner the presence of an atom is contributing only 1/8 portion. Therefore, 1/8 of atom multiplied by 8 such corners are there, right? So it will give you 1 atom per unit cell. So cesium chloride, you have a detailed study of cesium chloride. So cesium chloride is an example of a simple cubic. Similarly, how many lattice points are there per unit cell as far as a body centered cube is concerned in case of a BCC? So this unit cell, you just recall the diagram. Along with the 8 corners, you have presence of one lattice point at the center of the cube. So it has 8 corner atoms and one centrally placed lattice point or an atom. So number of lattice points belonging to this cube. So two types are there. One centrally located lattice point or atom, and second the same calculation. 8 corners are there. At each corner only 1/8 of atom is contributing to the unit cell under consideration. So 1/8 portion of atom, 8 corners, make it again 1 atom. So total number of atoms per unit cell, total number of molecules per unit cell, total number of ions per unit cell if it is an ionic crystal, right? So in general, number of lattice points per unit cell in case of BCC is 1 centrally placed lattice point plus, so 8 corners, at each corner only 1/8 portion is contributed. So in total it become 1. So 1 plus 1, it is 2. 2 atoms, that is 2 lattice points per unit cell. So 2 atoms per unit cell, 2 molecules per unit cell, 2 ions per unit cell, or 2 lattice points per unit cell in BCC. You have to remember always, because while solving problems, knowledge of this is required. Frequently you have to recall. The example is alpha iron. So third type of Bravais lattice, that is in case of a cubic system, FCC, face centered cube. So again you just recall the diagram. The unit cell of a face centered cube, it has 6 face centered and 8 corner atoms. So the 6 face centered atoms at the 6 faces of the cube, they are shared by their 6 adjacent cubes, because I mentioned if you take 8 unit cells together, you select any unit cell, it is shared with adjacent cubes. So at each face you have a lattice point where atom is there, it is shared between 2 adjacent unit cells. Like that you have 6 faces, right? Okay. So totally you have 6 facial points are there, that is 6 atoms divided by 2. This 2 is appearing because at each face is shared between 2 unit cells adjacent, right? So it makes 3 such atoms belonging to this cube, and you have a presence of 8 corners in this unit cell. At each corner you have 1/8 of atom is contributing to the unit cell under consideration. So the calculation is 6 by 2, it gives 3, and 1 by 8, that is multiplied by 8 corners, it is also equal to 1. So 3 plus 1 in total. Total number of atoms per unit cell of face centered cubic is 3 plus 1, that is equal to 4, and the sodium chloride is a best example of FCC, that is face centered cubic, and you have a detailed study of sodium chloride, frequently asked in the university exam also for 5 mark. And you can just observe the 3 pictures. The first one is simple cubic. You can observe at the corner for this unit cell only 1/8 of atom is contributing. So 1/8 of atom at a corner. So 1/8, 1/8, 1/8, 1/8, like that 8 corners are there. So in simple cubic 1/8 at each corner multiplied by 8 such corners are there. Therefore, 1 by 8 into 8, it gives 1 only. So, number of lattice points or number of atoms, number of molecules, number of ions per unit cell is only 1 in a simple cubic. That is what a simple cube is called a primitive cell. If a Bravais lattice having a number of lattice point per unit cell is 1, it is called a primitive cell. Look at the figure of a body centered cube. At the center you have centrally located lattice point where the atom, molecule or ion is to be located. So, at the central placed central atom is there, and again at each corner 1/8 of atom is contributing. Okay. So, one atom at the center plus 1 by 8 at each corner. Such type of corners are 8 in total. So, 1 by 8 into 8, it is 1. So, at the center you have 1. So, 1 plus 1. So, in BCC 2 lattice points per unit cell, that is 2 atoms per unit cell. So, this is FCC, face centered cubic. You can observe you have 6 faces. In the diagram, the 3 faces are appearing, the left one, right one and the top one. Likewise, bottom and behind and left. You can observe a semi, that is you can call it as a semi-sphere because it is divided or shared between the 2 adjacent, right. So, totally 6 faces are there. So, you have 6 facial atoms. Divide by 2 because only half the atom is contributed to this particular unit cell at every face. So, 6 divided by 2, 3 atoms, 3 facial atoms, and each corner again 1/8 of atom is contributed. Such type of 8 corners are there. So, 1 by 8 into 8, it is 1. So, 3 plus 1, totally 4 lattice points per unit cell. That is the case of FCC. So, the simple cubic, that is represented as SC. So, you can observe. So, at the corner, so primitive vectors, A is a primitive vector along X, along Y it is B, and along C it is along Z axis. C is a primitive vector, A, B, C, the edges of cube. So, at each corner lattice point where atom is hanged. So, this is simple cubic. Similarly, BCC, body centered cubic. You can observe at the corner atom, the entire atom is not belonging to this unit cell, only 1/8 of atom belong to the unit cell under consideration, and you have centrally located lattice point where an atom, a molecule or ion can be located. So, this is BCC. And the last one, face centered cubic. You can observe how it looks. So, at each face only half of the atom belonging to this unit cell, the remaining half belong to the adjacent atom. So, at each corner you can observe 1/8, 1/8, 1/8, such 8 corners are there. 1 by 8 into 8, 1 atom and 6 faces, only half is contributing, that is 6 into half. So, half atom at every face. Such type of faces are 6 in total. So, it is 3 plus 1. So, 4 lattice points per unit cell. Okay. And after this you have calculation of coordinate number and expression for atomic radius for these Bravais lattices, and then very important Miller indices. Okay. So, I will stop at this stage and I will take in the next class.